We thought we were doing personalized therapy 20 years ago. Nothing like personalized therapy is
It's
going
multifaceted, isn't
years
it?
from now.
So the question I have for you, for both of you, is what area of biology today do you think could most reshape cancer therapy over the next couple of years?
I'll start by saying I'm not an immunologist, but I am so impressed with what I'm seeing from my clinical colleagues using these T-cell engagers. They're basically, the concept is kind of like an antibody-drug conjugate. It's targeted against a protein that's expressed on the tumor cell, but it's bringing in the T-cells from the immune system instead of a payload.
Right.
And these are working in tumors that previously had failed to respond to the more famous form of immune therapy, checkpoint inhibitor therapy.
Can you give us a couple of examples, Charles, on that?
Well, I work in prostate cancer, and there's two examples that work quite well. One against a target called STEAP1, and another that is very recent against a protein called KLK2, which is a cousin of the famous prostate cancer protein PSA that's used to screen patients for prostate cancer.
And previously, I think prostate cancer was known as a cancer type that was a bit immune cold, right?
Yeah, some people have used the term immune desert to looking hard in a primary tumor for just one T cell. So the fact that this works in a very impressive way is quite frankly startling and surprising, but fantastic news.
Wonderful, thank you. What about you, George?
So I'll riff off that because I think what's going to change is our understanding of the so-called dark genome. It's very clear that these endogenous human retroviruses are in there and they pop up, and these represent things that tumors might have but other normal cells don't have. So if you look at that and then take the idea that we're looking for specificity, we're looking for something we can see on a cancer that normal cells don't have, and a way of targeting the immune system or anything else to those differences, this is a good example of that. Charles mentioned STEAP1. STEAP1 is also highly expressed in a rare sarcoma that we're very interested in, Ewing sarcoma. And so both prostate cancer, a very common disease, and Ewing sarcoma have this. We're very excited about a new study that's going to open using T-cell engagers to see if we can go after this in a disease similar to prostate cancer, where this bone cancer that spreads to lungs just hasn't had any benefit from any immune activators. So somehow we have to teach the immune system how to recognize this. And we'll learn more about the biology, because if you have this magical bispecific T-cell engager or bispecific antibody that's grabbing onto a T-cell here and a tumor there, how does that actually work? You know, do you really grab onto the tumor first and then wave your tail and then the T-cells get into the area, or do you tickle the NK cells to make some gamma interferon that then wakes up the environment so that the T-cells will sniff their way over there? Who knows? But we're going to learn a lot about basic biology at the same time we're learning about clinical biology and clinical care of patients. Really exciting times. We're still in our infancy of learning how to manipulate the immune system. In my world of sarcomas, almost all of the sarcomas do not respond well to any of this. And we know that the connective tissue landscape tends to be very immune suppressive. Is that because there's something about mesenchymal cells? Is that something else that's in there? Is it the macrophages that are tissue-derived that live there? We don't know. But this, I think, is going to change our understanding about how cancer starts, how it maintains itself, and how we can go after it.
Yeah, that's pretty exciting how T-cell engagers are making such a difference in solid tumors, especially on some of the very cold solid tumors. Besides T-cell engagers, anything else that come to mind in closing?
There's a lot of excitement around what are called protein degraders. So this is sort of pivoting from what I think most people are familiar with, which is you make a drug against a protein that is a cause of the cancer, a so-called driver, just by inhibiting its activity as an enzyme or whatever it does. Now it's possible to link, to make these proteins just disappear from the cell by basically creating a molecule that will direct the protein to the proteasome, which degrades the protein and destroys it. And there's a lot of evidence that these can have activity in places where standard inhibitors did not.
Not working. Yeah, taking a bad actor out completely, right?
Yeah, exactly.
Wow, great.
And I think as we look at our tools for diagnosing tumors, tumors aren't one thing. Tumors are very dynamic and they change over time. And one person's sarcoma is not the same as another. One woman's breast cancer or one man's breast cancer is not the same as somebody else's. And so as we look at a tumor, which is embedded in other normal cells, that spatial view is giving us insights as to how to use all these different tools. How do we deliver different things into that microenvironment the tumors are living in to really destroy them? You know, the number of cancers we can actually cure by the time they're spread is remarkably limited. But I think as we think about using some of these new technologies, delivery systems, antibodies, other nanoparticles that can be decorated on the surface to go to certain tissues, I think we're going to see a whole new range of things, but we have to understand the tumors, describe them, and diagnose them. We thought we were doing personalized therapy 20 years ago. Nothing like personalized therapy is
It's
going
multifaceted, isn't it?
years from now. That's what I think.
Are we ready for this complexity? I just have to throw that last question in here.
We're not, but AI is. I actually think this is where artificial intelligence will start to look at this, see patterns. It's up to us as the humans in the loop to really validate that and not just take it for granted just because NVIDIA and AI and Anthropic are giving us these answers. We always have to be the humans and say, is that answer real? And then we can validate it. And I think the science is up to that.
Great. Any last comment, Charles?
Well, I agree that AI is going to be a powerful tool for diagnosing the heterogeneity, but I still think we have a tall task to treat the heterogeneity. We're going to have to come in with combination therapies, and we've always known we needed combination therapies to combat resistance. Now we need to combat heterogeneity.
Wonderful. Thank you, gentlemen. Appreciate this time. Thank you.
Thank you.